Hi, I'm Julia Vitale, and this is my first lab for Physics 2211, Constant Velocity. So this is just a brief overview of everything I will be going over in this lab. First, I will start off with the introduction. So the purpose of this lab was to observe the motion of some object that is moving at a constant speed without changing direction, as well as comparing the movement of a pushed object on a table, which will just be an experimental model via tracker, to a computational model created with GlowScript. Some of the key assumptions that had to be made in this lab were that there would be no air resistance, no friction, and no external forces. The results of this lab was that the experimental model began to deviate away from the computational model and was not completely linear, which was most likely due to outside forces that were not taken account of. The key principle of this lab was Newton's second law, aka the momentum principle. Newton's second law states that the net external force equals the change in momentum of a system divided by the time over which it changes. So if there is no net force acting on the system, the change in momentum is zero and velocity will remain constant. Newton's second law can also be rearranged to produce both the position update formula as well as the velocity update formula. The procedures for this lab was to first record the motion of an object rolling at a constant speed in a straight line. So the object of this lab, or the system, was the expo marker, and the surroundings were everything external to the system. Then, import the video into Tracker software and track the position of the object at set time intervals. Manipulate the starter code in GlowScript to create a computational model of the object's motion, and then create position versus time graphs based on the data collected, and compare those two graphs. This is a video of the observed position of the expo marker. And if you look to the right, you can see that the position versus time graph appears almost linear, but we will check its linearity with the computational model. So in order to create our computational model, we will need a few data points from the tracker analysis. So we can see that when time is equal to 0 seconds, our position is 0.146 meters. And then when time is equal to 0.033 seconds, the position is 0.156 meters. So using the definition of velocity, which is just change in position over change in time, we can calculate that the velocity at this interval is 0.303 meters per second in the x direction. And we will just keep this the same throughout the entire computational model because we are assuming constant velocity. So here are a few snippets of code for my computational model. We can see here that I set the mass equal to 0.01. I changed the initial velocities and position to what we found in the tracker analysis. I set delta t equal to 1 over 30 as this was the time step of each frame. And then I set F net equal to 0 as we were assuming there is no net force. After graphing the points from both the tracker analysis and my computational model, this is what the graph ended up looking like. The blue dots represent the experiment position, and the red dots represent the model position. And as we can see, the model position is perfectly linear throughout the whole entire time interval because it is constant velocity. However, the experiment position starts to deviate as we get further along with time. So, why did this happen? Well, there are a few possible errors that could have been made. Firstly, we may have pushed the expo marker too hard, which led to a variable velocity instead of constant due to that acceleration in the beginning. Then, there could have been programming errors, wrong tracker inputs, wrong calibration, and differences in placing the center of mass in tracker. And the big one is that there were surrounding forces that weren't taken account for, such as friction, air resistance, and leveling of the table, among other things. Now, let's dive a little deeper into this lab with some further questions. The first one being, what if we were to change the axes? How would the results change? Well, if the axes were flipped, my graph would have a downward slope as the marker would be moving right, while that positive x direction is now designated as the left. So this means that the sign of velocity would be negative as position becomes more negative. However, my result wouldn't change because the magnitude of position is still the same, only the direction. And the second question is how many pushes or pulls to give zero net force? Well, it's not possible to say how many pushes and pulls are added together in this case because there are so many forces that weren't accounted for, such as friction, which was mentioned in the last slide. Thank you so much for watching.